The recording is now in progress. Good to see you all. A question you haven't asked me yet, but you can probably tell by my general demeanor of how good of a weekend I had hunting eggs with my son, enjoying this beautiful weather. No, your exams are not graded. Have I even started them yet? No, I haven't. But am I going to have them graded for you before class on Wednesday? Yes. Yes, I am. Alejandro. Why wasn't? Oh, why am I wearing a tie? I am on the presidential search committee for the new NSU president. You might not know this, our president is retiring in July. And so as part of my role of faculty council, I was in Tahlequah this morning, definitely not answering emails from the road to do that. I don't know why I'm in a tie either. These things are horrible. Why we do this to ourselves? I just feel like you're being choked constantly. Okay, so we have been talking, that's better. Hi. We have been talking about carboxylic acid derivatives, and I think I might end up giving up on section numbers for some of these because I'm just kind of collating parts of this chapter together. We are going to go through different reactions, but before I do that, I want to put up a list here of the reactivity of carboxylic acid derivatives. So as we go from amides should have asked, the proper answer to that should have been, why aren't you wearing a tie? That's right, gotta dress it up. Very formal event. This is an amide. I just got done saying it's no section. This is just a Dr. Green special. You didn't pick up on all of that within that rambling? You were stuck on the tie thing, weren't you? They're awful. Awful. This is an ester. I skipped over this one, but I'll put it in here just because you'll see it in some reactions. This is called a thioester. Oops. Blue. What's that? Anhydride. And remember, if I put an X on something, that is a what? Acid halide. Every one of the things in blue can act as a leaving group. Not all these leaving groups are created equal. If I kick off an NH2 minus, it's nowhere near as good as if I kick off an O minus, which isn't as good as if I kick off an S minus. And neither of those are as good as if I kick off this molecule that has an O minus, but with resonance, or over here as a halogen. The leavability of each one of these groups gets better as I go from left to right. And because of that, as I go from left to right, I get more reactive. Meaning on the other side, I am less reactive. With what? It's not about the bigness, it's about its ability to handle the charge once it gets kicked off. So that reaction I brought up, not Friday, Wednesday, about nucleophilic acyl substitution, where you have a nucleophile come in, make a tetrahedral intermediate, collapses, leaving group leaves. NH2, not a great leaving group, because it's not as electronegative as oxygen. Oxygen's not as good of a leaving group as sulfur, because sulfur is bigger and can spread the charge out. None of those three have resonance, so acid halide's even better than that. And the best are halogens, chlorine and bromine in particular, because they're very electronegative and they're very big. So we're comparing putting something on a chlorine versus putting something on two oxygens over here. Chlorine's a better bet, although both of these are quite reactive. That is to say, if I had an acid halide and an amide in a flask, and I added water to that flask, one of those things is going to hydrolyze much faster. The acid halide is going to hydrolyze like that, versus amides will stay in water for quite some time without hydrolyzing. That is a general overview of the reactions that we're going to be talking about. So what I'm going to do now is somewhat briefly and very much aggregate data, go through the reactions, first of carboxylic acids, and then through the derivatives individually. I am Do you have a copy of the book? Do you use the book? You better, because you're asking me about these sections, so you're the one that needs to be checking these out. If you look at the book, which is about 4 of you probably, you'll notice that this chapter is huge. It just takes up a lot of real estate. And so what I'm going to do is compress some of that, squish some of the sections together. I'll try and show you when I do that. But honestly, I don't have the best notes of like which parts I've done that with. So my bad. This section though is 21.3, which is the reactions of carboxylic acids. And I'm going to abbreviate that Q because carboxylic acid is way too long to write. All right, for each one of these, we're going to start with the carboxylic acid and we're going to turn it into one of the derivatives. You guys are not okay with this abbreviation. Everybody know what I'm talking about here? About half the room was going. You guys are pretty cool. So are carboxylic acids. All right, let's turn carboxylic acids into acid halides. Overly specific example from the book. I don't know why it needs all the methyl groups on there, but here we are. I can turn that carboxylic acid just said I wasn't going to spell it out, and here I am, into an acid halide, and in particular an acid chloride. Using what reagent? I think we talked about this. SOCl2, thionyl-chloride. Think of this as turning an OH into a Cl, just like we turned alcohols into alkyl chlorides. Thionyl chloride turns a carboxylic acid into an acid halide. Good. It's exciting stuff. Hearts and minds, that's what we're changing up here. Dr. Green, that's super boring. We already knew how to do that. What about turning a carboxylic acid into an anhydride? I'll do it right here. Why not? Let's just fill up the, maybe put this under like next thing. So to make an acid anhydride, from a carboxylic acid, there's actually a couple different ways of doing it, but if you're using just a carboxylic acid, and you wanted to turn that carboxylic acid into an acid anhydride, you can heat it up. I'm going to put triangle here, but really it should probably be like a triangle with like an exclamation point because the triangle represents 800 degrees Celsius. Gates of hell hot. Now, if I was going to make an acid anhydride, so this is again a carboxylic acid, and I was going to form an acid anhydride, I would not do it this way. The way I would go about it is I would take a carboxylic acid, take a proton from it to make a carboxylate, and then I would attack an acid halide. Do it in 2 steps. We'll talk about that a little bit later on with acid halide chemistry, but hopefully it's not too big of a stretch to see how I could turn this oxygen into a nucleophile. And then that nucleophile could attack another species. Don't write this down just yet, but that nucleophile could attack an acid halide. That plus that can make that. See what I'm talking about there? Ignore me, we'll come back to it. These are hard to read. You want to go outside too. I know, it's gorgeous. Questions about turning an acid, carboxylic acid into an acid halide or into an acid anhydride.
Is it 2 in front of the carboxylic acid?
Yes, it is.
Says-
Because I need 2 equivalents. This is acetic acid turning into acetic anhydride. So I need 2 equivalents of this to make that reaction go. What else would I lose from this? H2O. So water boils off of this. That's part of the get it so freaking hot part. Okay, we can also turn these into esters. We're still under section 21.3. Charles. Take my carboxylic acid. This is kind of what I was talking about earlier. You can turn a carboxylic acid into a good nucleophile. So the first way to do that is to add some base. Something like sodium hydroxide is a good choice. That would take the proton from this and make it carboxylate. And then in the second step, you need to give it an electrophile to attack. So something like methyl iodide. I wanted to add a methyl group to this. That is going to make 1, 2, 3, 4 carbons to the carbonyl. 1, 2, 3, 4. Carbonyl. Oxygen will be here. What else? Took the proton from that oxygen, made an O minus. O minus attacked the carbon, kicked off the iodine, and so now I just have a CH3 over here. I turned my Q group. Is he going to keep referring to it like that, like Cartman? Yes, he is. So I'm stuck in a loop. Into this. This is an ester. What's the name of this ester? What? Methyl butanoate for the win. Methyl being the group on the end, and then 1, 2, 3, 4 carbons, butanoic acid or butanoate is an ester. Make sense? This is what I was talking about earlier. You can turn a carboxylic acid into a carboxylate. Carboxylate is a good nucleophile, and then you can give it whatever electrophile you want. In this case, an alkyl group. So we made a carbonyl, oxygen, carbon, or an ester. I could do this similarly where I'd have a carboxylate attack an acid halide to have carbonyl, oxygen, carbon, anhydride. Yeah. Okay. One other way that you can do this, and we will do this, is the Fischer esterification. One of the last labs we will run in here. Well, wait, this isn't the lab we run, but we do a Fischer esterification in lab if you're taking that particular course. Reacts a carboxylic acid and an alcohol. Under acidic conditions, and this is very much a reversible reaction, so we're going to be careful about how much we heat these things. We often add heat. Oops. Nope. There. Let's name it this ester. Ethyl benzoic acid would get you pretty close, but we don't say benzoic acid, we say benzoate. And it's an ester. This benzoic acid is a common name for that piece. So if I said benzoic acid, that is a 7-carbon unit. the IUPAC name would be stupid. Benzene carboxylic acid would be the IUPAC name. Not good. Who wants to know how the Fischer esterification works? JJ does. I wasn't going to talk about it, but he wants to know. It's acid catalyzed, and if you've learned anything in this class, acid catalyzed reactions are a freaking nightmare. Let me show you said nightmare. I'm going to use a little trick here. I'll draw this once, and then I'm going to stop doing this. I'm going to start referring to this piece, the phenyl group, by the Greek letter phi. So that way we don't have to keep drawing cyclohexanes over and over and over. Hexagons, not cyclohexanes. First step of every single acidic mechanism you've ever seen in your entire life. Protonate something. Right? So we're going to have protons floating about. Actually, so a proton's not going to just be floating about. It's going to have something attached to it. I'm going to use hydronium as the carrier for it, because protons don't just float around in solution. They either attach to a Cl or most commonly water. The thing that we're going to protonate is this carbonyl. Here I am using my little shortcut. See how much faster that is? This, by the way, is super old school. People don't write like this anymore. I just think that it's a lost art. And so I'm bringing it back one student at a time. The way you'll see this most commonly written is with a pH, phenyl, like that. I think that's lame. So I'm going to use this one instead. All right, this is a activated carbonyl. It's got a positive charge up here. So it is very likely to be attacked by a nucleophile. The nucleophile we're going to use here is ethanol. How do I show that? Which lone pair? Ethanol. So this is my nucleophilic atom. It is going to attack the carbonyl carbon of the carboxylic acid, push the electrons up here, and make a tetrahedral intermediate. They all exclaimed with joy. You can't hear it on the recording over Zoom because it doesn't pick up the audio in there, but Natalie, everybody is just losing their minds. People were like standing up, clapping. Someone's in tears. It was beautiful. Approach with caution. When this oxygen attacks, students really want it to just look like this. You're like, all done. What did I screw up? Yeah, that alcohol had a proton on it. It's still there. Do I wish it wasn't there? Yes, I do. Is it still there? Yes, it is, with a positive charge. I need to get rid of said positive charge. This is a tetrahedral intermediate. So let's use water to do that. Since I brought up H3O plus earlier, then I have water here as well. Because if water takes a proton, it turns into what, Charles? Yeah, it does. Hydronium. I missed you guys. I was in this meeting with Buddy Duds all morning long. We were having like business speak and it wasn't good. And I was like, I got to get out of here and talk about some chemistry with my favorite people. Talking about like synergy and courage and vision and quantify. It's not good. It's not for me. I mean, courage and vision, fine. Anyway, so the next part of the synthesis is we need one of these things to go away. Look what's going on with our poor carbon here. There are 3 separate oxygens attached to that carbon. This carbon is unhappy. One of these things needs to leave. Now, I could get the ethoxy group to leave, but that wouldn't make much sense because I just added the ethoxy over here. So let's think about losing one of these OHs. Is OH a good leaving group? Yet. So how do I turn one of those into a good leaving group? Protonate it. Hydroxide is super strong as a base, meaning it's not a very good leaving group. But I'm going to take this one just so I can make it look nice and pretty. If I put a proton on there, now that's not hydroxide anymore. If I squint real hard and get rid of the positive charge in that bond, this is water, which is a fantastic leaving group. So I'm just going to push this off of here and never look back. Ren doesn't like it. Why not, Ren? Yeah, if I just kick this off of there, then I'm kind of messing with this carbon even more. Poor carbon has all these oxygens attached to it. It's very electron poor right now. If I take that bond with it, now it doesn't have an octet anymore. No good. I have lone pairs nearby that I can help out with this. I'm going to push the water off the molecule. The lone pairs from the oxygen are going to push down and kick off water. That way we don't mess with carbon in the meantime. Very similar. A lot of carbonyl chemistry is similar. Am I done, Charles? Do I have any more things I need to do? Carboxylic, or sorry, should I draw the ester over here? No. The tail. Anything else? Yeah, where?
I think that's lone pairs that would be negative.
Two lone pairs in this oxygen, yeah? So one lone pair over here now. Hydrogen on that oxygen. Still a hydrogen over here. Charge? What is it? Are you sure? Yeah, he's positive. Final step then to get this into a ester. What did I do? It's not my pen. There you go. Final way to turn this into an ester. Take the proton off of it. That's right. And if we use water to do it, we remake what? Miss McKillop? Hydronium, which is great because then we can keep our catalyst status. I'm going to put a blue box around this because I didn't use a plus space. And I also made H3O plus. That's why I used hydronium up here. It's just easier to be able to carry it back down. I think I brought this up before, but acid catalyzed mechanisms are a beast. And the reason is every time you're doing something in acid, you're always going to have to transfer a proton before you do the thing. So there's actually like two separate steps in here, right? Two actual chemical transformation. I'm going to do it over here. I hate standing behind this thing. Add a proton, remove a proton, add a proton, remove a proton. There are 4 proton transfer steps in here. This is an actual chemical reaction where two things react together. And this is an actual chemical reaction where we have an addition, elimination. Every other step in here is adding or removing a proton. So if and when I ask you to draw a mechanism under acidic conditions, and you freak out, because that's what happens when I do that on exams, I want you to take a beat and go, okay, what's the first step? I'm going to put a proton on something. If you do that first thing and you don't know what to do next, think about, well, should I take a proton off something else, right? Is there a proton exchange that can take place? Most of the time under acidic conditions, the answer is yes. I know this looks really complicated, but does everybody see how this first step is just adding a proton? This step is just removing a proton, adding a proton, removing a proton. You could just do plus and minus proton for over half this mechanism. Addition, elimination. Those are the two real steps. Questions about the Fischer esterification? The carbonyl oxygen would attack because that leads to a productive pathway. This oxygen can take a proton. There's just no meaningful pathway to follow there. Okay, let's see. So we turn them into acid. We turn carboxylic acids into acid halides, acid anhydrides, esters under a couple different mechanisms, amides. I'll put amides on this one. Kind of short. All right, so remember on that list where I showed you amides were on one side, sorry for you guys, amides were on one side, acid halides were on the other side. Amides are very non-reactive, acid halides are very reactive. To form an amide from a carboxylic acid, we have to put a lot of effort into that. Amides don't form directly. Well, I'll put don't easily form directly. The reason for that is if I wanted to turn a carboxylic acid into an amide, what would be the most direct route, you think, to do that? Add a carboxylic acid to an amine, right? So if I put an amine in here, I would want this nitrogen to attack that carbonyl. That is never going to happen. What is this nitrogen going to attack instead? The proton. This is an acid. Amines are organic bases. The only reaction that's going to occur between those two species is an acid-base reaction. So I could just show it like this. That would make a carboxylate and an ammonium. Well, if I want an acid-base reaction, great, but I don't. I want an amide. So I have to get more creative about how I would form an amide. And I think this is important to bring up here because amide bonds, I think I told you this previously, are also called what? Peptide bonds. They show up a lot in your body, in nature. Amide bonds are how nature puts together amino acids to make peptides, to make proteins. Proteins are the building blocks for better for worse. I would say carbon's the building block, but if I had to be a little more humble, I'd say proteins are the building blocks of life. This bond that I'm trying to make between these two things is hugely important. Our bodies, plants, other animals, excellent at making these bonds. I and other chemists are terrible at making these bonds in the lab. We don't have enzymes to put these things together. So we have to use special reagents to make amide bonds. The way we do that, sorry, I'm moving kind of quick here, is something called DCC coupling. Before I show you DCC coupling, any questions about why this is a bad idea? Doesn't form correctly, right? So when I was making an ester, I said, oh, I'll just add a carboxylic acid and an alcohol together with a little bit of acid catalyst. That works just fine, right? I replaced my OH with my alcohol. That same thing doesn't occur here because the nitrogen is so good at taking a positive charge, meaning that it's a good base. It can take protons. This ammonium is never going to attack a carbonyl. It has a positive charge, so it's not going to give electron density. So how do we get around that? We have to deal with the proton. So for that, we use something called DCC coupling. I'll pick on the DOS Purdue lab for just a second here. Do you guys do any synthetic protein work? Like, do you order up proteins? With like, but intentionally synthetic proteins. So you can order, you might not know this, you can order a protein. You can go through and say, hey, company, I want you to make me a synthetic protein because I'm trying to make a nanobot. All right, and they'll be like, well, I question your motives, but okay. So what you would do is you'd say, I want an alanine next to a glycine next to a something else, right? And what they would do is take each one of these molecules, do a DCC coupling and hook the next one on, do another DCC coupling and hook it on. So the chemistry is to attach a, here, actually, what's my example? Glycine and alanine. Have you guys memorized your amino acids? Yup. I did too. Ask me if I know any of them. Not one. I'm looking at my notes as I'm drawing glycine for you. This is glycine, so my notes tell me. And then alanine looks very similar to this, but has what? It does have a CH3. There. Okay, if I want alanine and glycine to form a bond, I need the NH2, the amino portion of alanine, to attack with the acid portion of glycine, but I can't just mix them together. So what I'm going to do is mix them into a molecule called DCC. I'm not going to go through this whole mechanism. Actually, I'm not going to go through any of this mechanism. DCC is a carbodiamide. I'll put it up here, just a portion of it. This is a carbodiamide. So that's an imide on this side, that's an imide on this side, but when we say that, we say diamide. DCC has a cyclohexane here. Feel free to not draw this if you don't want to, it's okay. Cyclohexane here, cyclohexane here. That molecule is called dicyclohexane carbodiamide. Diamide. I hate this with the two I's next to each other. So imide on that side, imide on that side. What happens is the carboxylic acid of one side of this attacks the carbon here to make an oxygen carbon bond. That gets rid of this proton and then allows the nitrogen to attack this carbonyl. DCC's whole mission in life, like the other big molecules we've shown, is to help us get rid of that OH bond. So what that gives us then, and if I wanted to do this specifically with alanine connecting to glycine, I'd react alanine and DCC first, and then I'd pour in glycine afterwards, is a nitrogen glycine bond there. This is my new amide bond, or as other folks in the biz call it, that is a peptide bond. Let me put that in parentheses because it's actually called an amide bond. Why everyone can't just call it what it is, I don't know. And in particular, this peptide that I made is a what? What's the parlance for amino acids? It's a dipeptide. Right? So there's two amino acids into this polymer. So this is what we call a dipeptide. These are amino acids. This is a dipeptide, also known as the world's smallest protein. When amino acids form a polymer, we call that a protein. This is about as much biochemistry as I ever want to talk to you about those, so I'm going to run away from this unless you have any questions. Yeah. Right?
Is this like something that we should like?
No.
carry on products page?
I could totally ask you about this on the products page. Yeah. Yeah. I mean, if you're asking me, like, am I writing this up here just because I enjoy writing in colors? I do, but I also want you to know, like, generally what's going on. I'm also assuming that you've seen something similar to this before. This shouldn't be blowing anybody's mind, right? In one of your biology classes, and everyone's taken biochemistry before or is taking biochemistry now. Jayla, are you shaking your head at me right now? Because right now you work in Okay, we'll talk about that later. Take biochemistry. This will be super second nature to you. The main thing here is don't get distracted with all this other stuff. I have a carboxylic acid, and an amine reacting together. All the other stuff is just hanging on there to make amino acids. You see that part? Carboxylic acid plus DCC plus amine makes amide. Amide, also called peptide. Circle everything, you circle them. Cool. Okay, Charles, this next section is section 21.4, 5, and 6. We 1.4 through all of them. Through 4.6. And that is the chemistry of acid halides and hydrides and esters. Why am I combining all three of those together? Because they all have the exact same reactions. Acid halides and hydrides and esters. I want to try and put all this in there. Sure, why not? Okay. In the middle here are our starting materials, acid halides. I've been doing these in blue, haven't I? Acid halides. Acid and blue. Acid and hydrides. And esters. If I mix any one of those things with water, what do I make? A carboxylic acid. This is a great nucleophile. Everything in blue over here is a great leaving group. Oxygen's going to add, make a tetrahedral intermediate. Protons will change hands, tetrahedral intermediate collapses. Thing in blue leaves. I'm left over with what was attached to the oxygen, which is an H, actually a couple H's at first. And that leaves me, of course, with a carboxylic acid. What kind of reaction made my Q group? Hydrolysis. All right, I'll stop saying Q. You guys don't think it's funny anymore. That makes sense? Good nucleophile, good leaving groups, swap places. Yeah. All done. Well, of course, I got two more things. That wouldn't, I mean, that is like very much how I write, you know, it's like squish everything in a corner and then leave a bunch of big blank space. Let's do, I think Charles just volunteered for this next one. If I react first with a hydride source, I'm gonna just, no, I'm not. I'm gonna write sodium borohydride. Sodium borohydride could also be lithium aluminum hydride. And I followed that up with acid and water. For react any one of those three, first with a hydride and then follow it up with water. Mr. Cruz, what do I make? At first, I would make an aldehyde, but aldehydes are still very reactive to hydrides. Do it once. Yeah. What she said. Make an alcohol with 2 additions of the hydride. And in particular, this would be a primary alcohol, right? I don't know why everything's in green all of a sudden. This is a primary alcohol. That is a carboxylic acid. Every time we talk about hydride chemistry, we have to talk about Grignard chemistry too, because if you can add an H- to something, you can add a C- to that same thing, and the chemistry is effectively the same. The products are different. Let's use methyl Grignard, CH3 MgBr. Have to have an acid-water workup. I mean, it can just be water workup, but adding a little bit of acid makes it faster. Too much acid makes it explode, so just a little bit. What am I going to make down here? On top, when I made a primary alcohol, down here I will make a tertiary alcohol. First thing that's going to happen is Grignard's going to add to any one of these. Let's use the acid halide. Grignard adds, makes a tetrahedral intermediate, O minus. O minus pushes down, kicks off the chlorine. Now I've made a what? A ketone, which is still reactive to Grignard. So the Grignard attacks that again, and just like the hydride did, we have two additions of the Grignard. And that is then, of course, a tertiary alcohol. I went pretty fast through both of those because we've seen both of those chemistries in the alcohol chapter, chapter 18, a while back. Been a minute. How we doing? Good stuff. Okay, I don't know if you're gonna like this next graphic or not. I'm a little on the fence on how I feel about it, but I'm gonna show it to you and maybe it'll work with you. If you hate it, or if you're like, and then just ignore it, right? But if it's helpful, yay. It's kind of interesting. What we're gonna do is graph, not even really a graph. As I go up this way, this is gonna represent increasing reactivity. My handwriting was so good normally, so I thought I would turn it vertically here. If you're at the top of this list, you're going to be very reactive. If you're at the bottom of this list, you're not going to be very reactive at all. Going from the top to the bottom is a natural thing, right? Just like water rolls down, or poop rolls downhill, right? Water also rolls downhill. Reactions will go from highly reactive molecules very easily to lower reactive molecules. At the top of my list is going to be an acid chloride, the most reactive acid derivative. At the bottom of my list is going to be an amide, the least reactive carboxylic acid derivative. So I can turn an acid chloride into three different things. Again, if this helps you, great. If not, don't worry about it. If I react an acid chloride with a carboxylate, what is that going to make? An ester. That's my nucleophile, O minus. That's my leaving group. And a hydride, very good. If I react an acid chloride with an alcohol, what's that going to make? An ester. And if I react my acid chloride with an amine, what's that going to make? An amide. This is supposed to be a little bit lower. It's okay. I sure do. Sure do. More busy thinking about my color scheme than actual like information on the slide here. Yeah, I'm going to move this down just a little bit. Sorry. Don't move it in your notes. It's not that big of a deal, but I'm trying to make this graphic as helpful as possible. So that's supposed to be high up, a little bit lower, lowest. Fine. I'm running out of colors though. Let's see, this was ester in red. And then orange, fuchsia, amide. You guys all have bright pink pens, right? You're good to go. Some of you do. Some of you have like the mega pack. Okay, I can turn an acid chloride into an acid anhydride, into an ester, into an amide. It's very reactive, which means I have lots of options of how to turn these things into one another. Turning an acid anhydride into an acid chloride is very challenging. I'm going uphill in energy to do that. I'm turning a more stable molecule into a less stable molecule. Hard to do. Turning a less stable molecule into a more stable molecule, easy to do. What if I wanted to go from, here's where the colors are going to get real fun. What if I wanted to go from an acid anhydride to an ester? What would I react it with? Same thing. Look at that. How convenient is that, right? Alcohol plus acid anhydride makes an ester. What if I wanted to turn an acid anhydride into an amide? React it with an amine, right? I can't put these names on there. It's gonna get here. I'll just do it this way. Carboxylate. So acid chloride plus carboxylate makes acid anhydride. Acid chloride plus alcohol makes ester. Acid chloride plus amine makes amide. Acid anhydride plus alcohol makes ester. Acid anhydride plus amine makes amide. See how this is flowing?
So acid anhydride plus alcohol makes ester.
Acid anhydride plus alcohol makes an ester. Yep. Acid anhydride plus amine makes amide. Ester can turn into an amide by reacting with what? An amine. So acid chlorides can turn into amides. Acid anhydrides can turn into amides. Esters can turn into amides. Amides are really hard to turn back into esters. They are even harder to turn back into acid anhydrides. And if you want to turn an amide into an acid chloride, find a new job. The reaction is not going to work very well at all. How do we feel about this maybe overly complicated graphic? You like it? Stole it from your book. I'm with you. When I saw it, I was like, that's catchy. I'm not really picking up on it though. I like the colors. The colors are nice. Okay, I could show you every one of these mechanisms, but I'm not going to because you will all hate me more than you do right now, and it would take forever. So what I'm actually going to do is shut up because I only have 2 minutes left, actually 1 minute and 10 seconds left. So I'm going to give you a minute. And then on Wednesday, we are going to talk about one reaction, which is turning a ester into a carboxylic acid, showing how these things fall apart to make different carboxylic acid derivatives. We'll leave it there for now, and I will see you all on Wednesday.